In this lab, we observe the motion of an object dropped from rest that falls somewhat slowly to play around with Newton's second law of motion, that the net forces on an object are the result of its mass multiplied by its acceleration. So if we take a look at the tracker video real quick, we see that we have a piece of tissue paper initially at rest that is dropped and it falls. Why is it falling? Well, let's say it's falling because of gravity, right? And that the only force acting on it here is gravity. Let's model that real quick. So we have the code here, and you'll see that it starts at rest, and the net force on the object is going to be gravity times its mass. So let's run it, and we'll see that the final position is negative 2.5. All right, let's go back to tracker and see if this matches up. Nope, not at all. Negative 1.5 is our actual observed distance traveled. So, obviously, gravity isn't the only force at work here. There's some force going upwards, and we are considering that force. We're calling it drag. And the drag is equal to some constant times the velocity squared. We don't know the constant, but we can get it from our observed data. And so, when we go model this situation once again with drag, we will see that I ended up with a constant of 0.000261. And in this code, the net force is the force due to gravity plus the force due to drag on the object. So we have the constant times the velocity squared. And so let's run this situation, and we'll see that we end up at negative 1.58. Now, this matches up. And now we have a much better representation of what's going on, a much more accurate to real life representation. And so now when we go into Excel and we model them, clearly the no drag does not model the situation well at all, but the model with drag is modeling it quite well. They match up nearly exactly. There's a little bit of deviation here, but that could always be because of auto tracker not getting it exactly in the middle every time. And since the tissue isn't the same size as this little dot, sometimes you can see it's getting above, sometimes it's getting below on the tissue. It's not 100% accurate, but through the spreadsheet we can see that it's close enough to the real world. The real world is close enough to the model, and so we can say that they match up quite nicely. And so when we go back into the model, you'll see that what's happening here in the example with drag is that the velocity is evening out over time. It's not constant, it's leading to a constant. And then, so the change in velocity is becoming zero. The overall acceleration of the object is going towards zero. But in the model without drag, this acceleration is constant. The slope is constant. And so, what we see is that the drag force is equaling the gravitational force. And that's why we see this evening out of the acceleration. But what if the object was initially thrown? So let's try that. What if it starts with a velocity of negative 2? Let's run the situation, and we end at around negative 3.11. Let's try with negative 5. We're throwing it a little harder this time. Once again, we'll see it's around negative 3.11, right around there. Let's go back to the initial 0. Let's see that it matched up. Once again, around the same place. So what we see is that no matter what the initial is, no matter what the initial velocity is, the forces even out in the end. The force of drag evens out because it's a result of the velocity squared anyways. And that's about it. Thank you for watching.